In this lesson, we analyze the relationship between two random variables. The relationship between the random variables x and y is described by their joint probability density function. This is the definition of joint probability density function. It is a 2D, two-dimensional function of A and B, and it is the ratio between this joint probability. It is the probability of the intersection of these two events. The first one is the random variable x between A and A plus the A, and the second event is the random variable y between B and B plus the B. As all the 2D function, it can be represented in 3D in this way, and the volume under this surface is of course 1, since it includes all the possible events, so probability 1. In each position of this 3D surface, you have the probability, the joint probability of x and y in the interval dB and dA. But since often it's difficult to analyze the 3D plots, it is convenient to have also a 2D representation where we use a color scale or a gray scale to indicate the value of the probability of the joint probability density function. Strictly connected to the joint probability density function, there is the conditional probability density function. This is a really important tool in computation of probability and in the estimation theory. The relationship between this conditional probability of the variable y given the value of x is this one. It is resemble what we have seen for the probability and the conditional probability and the joint probability. In order to realize this relationship, we can have a graphical view of what happens when we write down this equation. We start from the joint probability here, then we fix a value of one of the variable, in this case x equal a, and we read the conditional probability just by reading the joint probability along this axis here. So at fixed x equal a, and you obtain this function here, that is 1D function. Of course, since this function should have a unit area, we have to normalize, and the factor that normalizes this area to 1 is the division by the probability density function of x in the value a. Well, there is a special case of independent random variables. Just to summarize, we have that the joint probability density function equals the conditional probability times the probability density function of x. And if the two random variables x and y are independent each other, that is, one has no effect on the value of the other, then the conditional probability of y given x is exactly the same of the probability of y without any condition, because there is no influence on one variable on the other. So in this case, and I emphasize only in this case, only if two random variables are independent, the joint probability density function here can be written as the product of the probability density function of y times the probability density function of x. There are important consequences of independency of random variables. The first one is that the joint expectation value, the expectation value of the product, is the product of the two expectation values. And another important consequence is that the expectation value of the conditional variable is the expectation value of the variable itself. Why is this so important? Because this conditioned expectation value is the best prediction of the value that the variable y will take given the value taken by the variable x. This is the best estimation in the sense that it minimizes the mean square error. And in case of independence, and so when the conditioned value, expected value, equal the expected value of the variable y, there is no advantage in knowing what happened in x, since x tells us nothing about the value that y will take. Let's see a couple of examples of random variables. Let's start with independent random variables, then we shall see something about the dependent random variables. And we use again what we have seen in the previous lesson, a random variable that is the position of a marble running with constant velocity along a path L meters long. And we have two of these variables, independent one from the other. So the two marbles are moving independently one from the other. And we already know that the probability density function of these two random variables, x, the first one, y, the second one, are both uniform between 0 and L. And since they are independent, the joint probability density function, what we have said before, is just the product of the two. And so we have 1 over L times over L. So we have 1 over L squared. And we have the multiplication of these two rectangles here. But the two rectangles are on orthogonal axes. And so, in conclusion, we have a constant 1 over L squared on a square basis, and the square as side L, capital L. So this is quite simple when we have to handle independent random variables. Things are not so simple where we have dependent random variables. And we see this example. Again, we have the two marbles moving independently along their path as before, but now we are interested in the joint probability density function between x and this new variable z, that is x plus y. Of course, x and z are dependent one from the other, because z contains also some information about x. We introduced it by using this sum here. So we analyze and we compute the joint probability density function between x and z by using the conditional probability of z given x times the probability of x. Here I used the parameter, the variable c for the variable z, in order to have no confusion with the b I've used before for the variable y. Let's see how we compute this conditional probability. Well, it is quite simple, because since z is y plus x, given x equal a, we have just to substitute x with a. And so the conditional probability of z given x equal a is the probability of y plus a here. And so the probability density function of y plus a, that is the probability, the conditional probability of z given x, is just this uniform probability, not from 0 to L, but from a to a plus capital L. And so, if we now generate the plot of the condition, the joint probability of x and z, we obtain again 1 over L times 1 over L, so 1 over L squared, a constant. But now the constant is not on a square basis, but it is on this basis that is a parallelogram, which has dimension L along the A axis and 2L along the C axis. Another important consequence of the joint probability density function is that we can compute the probability density function of the two variables just by integrating the joint probability density function along the two axes. And in particular, if we integrate the joint probability density function along one axis, we obtain the probability density function of the other random variable. Let's see in our example. We have z and x as random variables. We already compute the joint probability density function of x and z. Now, if we integrate this joint probability density function along C, that is, if we integrate along this axis here, what we obtain is the probability density function of x. And you see that by integrating along this axis, whichever is the value of a, we obtain just 1 over L, because there is a constant 1 over L squared integrated over L, it is 1 over L. And we obtain the constant value 1 over L from 0 to L. But we already knew that, because we already knew which was the probability density function of x. Different story for the probability density function of z, because we have to integrate on the other axis. And if we do that here, we see that what we obtain along the C axis is this triangle here. This triangle, because by integrating for C equals 0, you obtain 0. We have nothing here. We have all zeros along the integration axis. In capital L, we have 1 over L, because we have 1 over L squared integrated over L. And again, we have 0 in position C equal to L. And this result is quite interesting, because it indicates the probability density function of the sum of two independent variables.